I'm going to do the photoelectric effect now, which goes along with the nature of light. Light is a particle PowerPoint. I'm actually not going to put the PowerPoint up. I'm just going to kind of teach this to you freehand, freestyle, and then we'll go from there. So I've also got an animation to show you, so I don't know how much of this is going to fit on one video, so it may be split over a couple of videos. So this is all about the photoelectric effect. So that's what this is going to be about. Now, a couple of things just at the beginning. First of all, the photoelectric effect shows us that light behaves as a particle. So that's really what it's all about. And it was first proposed in 1905 by Einstein. And it was more of a thought experiment for him. It was kind of an idea he had about how light would behave. He didn't really do he did a lot of the math behind it, but he didn't run the experiments part of it. That was done by somebody else. But he had this idea that if you shone light onto a surface, that it could release electrons from the surface. And so we say that when we see that happening, that light is behaving like a particle because it's bumping the electrons out of the place. And that would be something that a particle would do. So we need to do a couple of just definitions to make sure we're good. A photon is basically a particle of light. So that's what we're going to use. That's the word we're going to use for photon. For a particle of light, we'll use a photon. And it is, if you want to think about it, it's like an energy bundle. It might be the best way to think about what it is, because light is a wave bundle. But it's kind of like a little packet of energy. When we draw them, we usually draw them like a little arrow with a little wavy arrow so to indicate that it's a wave, but also that it's a particle. It does have a frequency, so photons have frequencies. Those frequencies are going to measure in hertz, and that frequency would correspond to the frequency of the wave, and it will have the energy being the Planck's constant times the frequency, and that's a formula that you are aware of and you're familiar with. That energy is going to be in one of two different units. The first unit is joule, and that's the one I think you're most familiar with. And when you're going to use the Planck's constant that's in joules seconds, that I think it's 3.34 times 10 to the something, you know it. It's that one. When you use that one, you get your energy in joules. The other option is you can have the energy in a unit called an electron volt. And an electron volt is related to a joule because the conversion is 1 electron volt is 1.6 times 10 to the minus 19 joules. So you can convert back and forth. Since the joules are such small numbers, they're usually 10 to the minus 18, 10 to the minus 19, 10 to the minus 20 joules. If you divide by this number, 1.6 times 10 to the minus 19, you'll get an easier number of electron volts. So an electron volt is a unit for energy. It's defined as the amount of energy that an electron would gain if it moved across a 1 volt gap. So if I had a gap of 1 volt and I were to take an electron and move it across that gap, it would gain a certain amount of energy. It would be sped up a certain amount, and the amount of energy it would gain would be considered 1 electron volt. So that's how we define what the electron volt is. So just be aware that sometimes you will see the energy of the photons given in joules and sometimes in electron volts. All right. So what is this photoelectric effect all about? Well, here's what ends up happening. You start with a metal surface. So you have some sort of metal, and at the surface of that metal are some electrons that are just minding their own business. Okay? And then you're going to take a light of some form, and you're going to shine that light down on the surface. And so that means that there's going to be little photons that are traveling from the light and that are going to come down and they're going to hit the surface. Now, if those photons have a high enough frequency, they can actually cause the electrons to bump out of the surface. The electrons can actually exit the surface if the photons have a high enough energy. Okay? So what will end up happening if you're running an experiment is if you start with a low energy light, the low energy light will just come down and be absorbed by the surface, but it won't be enough energy to actually eject the electrons. You have to actually reach a certain frequency. That frequency is called the cutoff frequency. We have a symbol for it, F0. If these photons that are coming in have a high enough energy, so that their energy is equal to h times the cutoff frequency, then that will cause these electrons to be ejected from the surface. Okay? If you run the same experiment, but you send in photons with energy that is less than the cutoff energy, then these electrons, they may start to vibrate in place more, but they won't actually be ejected from the surface. They don't have it. This is not enough energy to cause them to be ejected. There is a certain amount of energy needed to break the bonds of those electrons with their atoms, and once you reach that energy, which is called that cutoff energy, then those electrons will actually, will be ejected from the surface. What happens if you shine a light that is more energetic than the cutoff frequency? So let's suppose I shine some high energy light on the surface so that the energy of this is greater than the cutoff frequency. Then what's going to happen is, of course, the electrons will be ejected, but they'll have extra energy also. So not only will they be ejected, but they'll be ejected quickly. They'll have some extra kinetic energy. So if I can shine a light that has a higher energy on it, the electrons get ejected and they have a certain speed. And their amount of speed is depending on how much kinetic energy they have. So if we just look at this from a conservation of energy standpoint, we have energy coming in, we have a certain amount of energy needed to break the bonds, and then we have the energy coming out. And we should find that if we do a summation, those should all be equal. So the energy in should equal the energy needed to break plus the kinetic energy coming out. And that's what you have, basically. Now, to define some words, there's something called the work function. The work function is the energy needed to break the bonds. So this is the amount of energy that you need to break the electron out of the metal. And since this work function, we have a symbol for that, it's W0. And since it's equal to the minimum energy, it's equal to this amount of energy right here, that's what the light would need to be in order to break the electron out of the metal, the cutoff frequency times h. So that's going to be our work function. So what we said using conservation of energy is that however much kinetic energy the electron exits the surface with is going to be equal to, that's not a negative, by the way, that's the electron, sorry, is going to be equal to the incoming energy of the light minus the work function of the surface. Okay? So just to define, this is the kinetic energy of the electron once it ejects from the surface. This is the incoming energy of the light. And this right here is the work function. That's what you require to get just to get the electron to break the surface. Okay? So you can see, if we go ahead with this formula, and let's suppose plug in for the work function HF0, right? So you can see that any F value, any incoming energy greater than F0 will give the electron some kinetic energy. But if you have an F value that's equal to F0, then there will not be any kinetic energy. The electron will just be released from the surface, so it'll just break free, but it won't actually go anywhere. If you send in an F that's less than F0, the electron actually can't go because it can't have negative kinetic energy. So you have to have an F greater than or equal to F0 in order to actually break the electron off the surface. So that's the whole idea behind the photoelectric effect. Before we do any problems, I'm going to move to an application of this, but I'm going to stop the video here and we're going to pick up the application in a different video.